Hey guys, so in this question we have an infinitely large layer of charge of uniform thickness T, right? So here one thing to notice is we don't have a infinite sheet. We have an infinite plate kind of thing. We have an infinite plate kind of thing where the length is infinite, breadth of this is infinite, but the thickness of this layer, there's a thickness to this layer, and this thickness is T over here. So an important thing to understand this is not like an infinite sheet. This is like a infinite plate, we'll say. This is like an infinite plate right now, right? Okay, so you have an infinitely large layer which has length infinity, breadth infinity, but thickness is T. So this is like the side view of the diagram. You're looking at this layer from the side, and this infinitely large layer of uniform thickness T is placed in an existing uniform electric field. So there already was an electric field before, and now you're bringing this infinite large layer into this electric field. So because of this charge layer, this will alter the electric field right now. Because this consists of charge, your electric field now in this region will be due to the already existing electric field plus due to this layer as well, right? And presence of this charge layer alters the electric field such that it remains uniform on both the sides. So electric field is still uniform on both the sides, and it assumes values E1 and E2 as shown in the figure. So your value of electric field over here is E1, your value of electric field on this side is equal to E2, on the right of this layer is equal to E2. E2 value is given. So from this we need to calculate what's the x component of external field in what's the x component of external field in x direction, right? Okay, so in this question we'll be learning a new formula basically, and the formula we need to derive for this is we'll have to derive the formula for electric field due to a infinite charge layer, which is what we have in this question. We need to derive the formula for electric field at an infinite charge layer. So that's the formula we'll be deriving first. So let's go ahead with this derivation. Let us start off with this derivation. Okay, so let me define the scenario. So in this case I'm drawing the same diagram. I have an infinite charge layer. So your length of this infinite charge layer is infinity, your breadth of this infinite charge layer is infinity, but your thickness is T right now. Your thickness is T right now. So this length is infinity, even this length is also infinite. Even this length is also infinite, is what hopefully you've understood from the question, right? Now what we'll be calculating is, we'll be calculating what will be the field due to this infinite charge layer. And even though we only need the field outside here, let's derive both the formula. We'll derive the formula for field outside as well as inside this infinite charge layer, right? And the way we derive this is by making use of Gauss law, right? So let's say I need to calculate electric field at infinite charge layer first at a point P, and this point P is located r distance away from the axis, and your r is less than T by 2, which means it's located inside this infinite charge layer, right? So here we'll be solving this. Here we'll be deriving this field from Gauss law. So the Gaussian surface we'll be taking over here is a cylinder. We'll be taking a cylinder. The length of the cylinder will be 2r. The length of the cylinder will be 2r, and the area of cross section of the cylinder, let's say, is equal to A, right? And now from symmetry, I know that electric field lines everywhere over the cylinder. The electric field lines everywhere over the cylinder will be like this. And because this is an infinite layer, every point is like the midpoint. So electric field first of all has to be horizontal, and electric field value everywhere will also be the same over here, even on this side as well. Right, now let's make use of Gauss law, and that is integral E bar dot dA bar over this Gaussian surface will be equal to charge enclosed by epsilon naught, right? What will integral E bar dot dA bar here become equal to over this surface? So I won't have any flux to the curved surface area. I'll only have flux to the base areas. I'll only have flux to the base areas over here. So this integral E bar dot dA bar will just become equal to E into A over this surface, E into A over this surface, and E into A over this surface. So this value will become equal to 2E into A, and that will now be equal to charge enclosed into epsilon naught. How much charge do I have enclosed? The charge enclosed here is nothing but the charge inside the cylinder. So that will be charge density multiplied with the volume of the cylinder, which is equal to nothing but pi into, or in this case, since we wrote in terms of area of cross section, it will be rho into A into length of the cylinder is 2r. So this will be your charge enclosed divided by epsilon naught. So from this, what will we get the field value? We'll get the field value to be equal to, so 2 and 2 gets cancelled. We'll get the field value to be equal to, A also gets cancelled. So we'll get the field value to be equal to rho r by epsilon naught, right? So what we have derived right now is we derived the formula for field due to an infinite charge layer for a point lying inside the layer. So this point was lying at a distance of small r from the layer, so we selected a Gaussian surface this way and we got this answer, right? So I'm doing this derivation. This is one of the derivation which can be asked as a numerical as well. But this was irrelevant for the question. Now let's actually go to the question. We need to calculate field to this infinite charge layer for points lying outside this layer. So as you can guess, we'll have to once again use the same idea. We'll now have to calculate what's the field due to this charge layer at a point P, which is now lying outside the layer. So let's say this point P is lying at a distance of r from the central line of this layer, and here r is greater than t by 2, which means we are outside this layer right now, right? So once again we'll make use of Gauss law. We'll take a Gaussian surface, and the Gaussian surface is cylinder. I'll be once again selecting a Gaussian surface of some area of cross section, and your length of the cylinder I'll say will be equal to 2r right now. Your length of the cylinder now is equal to r this way as well as r this way. Both these points will be symmetrical, right? How will your field lines be? Since it's an infinite layer, your field lines have to be horizontal, so your field lines will be this way, and electric field at all these points will be same. So now making use of Gauss law, we'll write integral E bar dot dA bar will be equal to charge enclosed divided by epsilon naught. So integral E bar dot dA bar, that is flux through this closed surface, will be equal to, I'll only have flux through this space, I'll only have flux through this space. So this value becomes equal to 2 into E into A. And what will be my charge enclosed? Now I don't have charge enclosed within the entire cylinder. I only have charge enclosed in this portion, right? And this portion will also be a cylindrical portion. So your charge enclosed here will be equal to rho into area of cross section into thickness. So the volume of this cylinder basically divided by epsilon naught. So from this, A gets cancelled. So what will you get the field value to be equal? We'll get the field value to be equal to rho t, right? 2 epsilon naught, right? So this is the formula which we'll be making use of to solve this question. That is, field due to an infinite charge layer for points lying outside the layer will be equal to rho t by 2 epsilon naught, and if it's partially charged, it will be away from it, right? So with this kept in mind, let's start solving this question. Okay, so according to our question, we already had an electric field existing. So let your external electric field have an x component, let that x component be Ex, and let's say it had a y component as well, let your y component be Ey. So this was the external electric field which was already present. And now inside this external electric field, we are bringing this infinite charge layer. Having a thickness T, having a charge density rho, right? Okay, so now because of this infinite charge layer, there will be a field created by this layer in this way. There will be a field created by this layer everywhere here. If you notice, the field outside was uniform. So field due to this layer will be created everywhere in this direction towards left, and field everywhere here will be created this direction towards right. So what will be a net field towards left right now? So can I say net field towards left in the left region will be equal to nothing but Ex minus rho t by, so using the formula which you derived, rho t by 2 epsilon naught I cap plus Ey j cap is the net field now you'll have at the left. And if you notice, this term was already uniform. Ex and Ey are constants over here because it was mentioned our external field was uniform. Now you have to add the field to this layer, which is also a uniform thing. So your net field in the left is a uniform field itself, and that will have this value. What will be your net field towards right? Your net field towards right now will be equal to Ex plus rho t by 2 epsilon naught I cap plus Ey j cap, right? And now it's mentioned that field in the right has, so field in the right is mentioned in this question as E2, and that is making an angle of 60 degrees with the horizontal, right? And field in the left was E1, and that was making an angle of 30 degrees with the horizontal. Okay, so now one idea we can use already is we know that y component of field over here, sorry, I had to write this here. So we know that y component of field over here is same. Field over here was E2 making an angle of 60. Field over here was E1 making an angle of 30 degrees, right? So we can write E1 sine 30 is equal to E2 sine 60, and both these values are equal to Ey. right? So from this, we didn't need to find out, but there's also an information which we can get. So here we'll get E1 by 2 is equal to 20 into root 3 by 2, which is equal to EY. So from this, EY value is 10 root 3 is one information we get. But what is E1 value? We'll get E1 value to be equal to, so 2 gets cancelled. We'll get E1 value to be equal to 20 root 3. E1 value to be equal to 20 root 3, right? Okay. So now what's your x component of electric field in the left side? Your x component of electric field in the left side is Ex minus rho t by 2 epsilon naught. And that value will now be equal to E1 cos 30, which is equal to 20 root 3 into root 3 by 2. So that will become equal to 20 into 3 by 2, which is 30. Similarly, what is your field on the right hand side? That is Ex plus rho t by 2 epsilon naught. So that will be equal to E1 cos 60. Sorry, E2 cos 60, which is equal to 20 cos 60. So 20 into 1 by 2. So that value will be equal to 10. Right, so now if I add both these equations, your rho t by 2 epsilon naught gets cancelled. So you'll get 2Ex is equal to 40, which means that your x component of external electric field will be equal to 20 in this case, right? So a new concept in this question, or rather I'll say a new derivation in this question, and the derivation which we had to understand over here is what's the electric field in an infinite charge layer. So we derived this for both inside and outside because I wanted to do this derivation properly for both the cases. We had to make use of the outside case only. We saw that electric field to this infinite charge layer outside was uniform, and then we made use of this to solve this question, right? So hopefully this question made sense. See you guys in the next question.